All right, so you will learn more about this in a course on communication system. Okay, but this is just to give you an example of how this multiplication property may be useful in practice. Okay. All right, so another example, computational-wise, is this example here. Okay, so in this example, right, we have this signal x of t that is equal to sine t times sine t over 2 over pi t squared. Okay, and we're asked to find the Fourier transform of this. So this signal looks a little bit complicated. Okay, but actually, you can view this signal as the multiplication of two sinc-like functions. Okay, so you can view this as sine t over pi t times sine t over 2 over pi t, and I need a pi here to cancel out one of the pi's. Okay, so you can actually view x of t as a scale of the multiplication of two sinc functions. Right. So if you observe this fact, then you can see that this may be easier. The Fourier transform of this may be easier to compute by first computing the Fourier transform of these two and then performing the convolution. Okay? So by the multiplication property, okay, the Fourier transform of x can be written as can be written as 1 over 2 pi times pi of the Fourier transform of sine t over pi t convolved with the Fourier transform of sine t over 2 over pi t. Okay? Now the pi cancels out, so this is 1/2. The Fourier transform of the first signal is just a square from -1 to 1. Okay? And the Fourier transform of the second one is just a square from -1/2 to 1/2. Okay? Okay. So in this case, right, computing the convolution actually is easier than computing the Fourier transform of the product. Okay? Because in the frequency domain, we have two very simple, square functions. So computing the convolution is easy, right? We just take the square function, we slide it through. Okay? So before they touch each other, the convolution is 0. Once they start to touch each other, right, the convolution increases linearly until they overlap completely. Right? Once they overlap completely, the convolution is just the area of this square, which is 1. Right? So I remain at 1 over this period, and then I start to decrease again, and then go to 0. Okay? So if you work this out, you will get something like this. Okay, so next, let me skip over the next few slides here that talk about how to implement variable center filtering with variable center frequency. Okay, so this is just, sort of a side note to show you how you would practically implement a variable frequency filter. Okay, but this is not really relevant to our studies. Okay, so let me skip over this. So in this chapter, we mainly showed how to extend the Fourier analysis from periodic continuous time signals to aperiodic continuous time signals. Okay, so basically, aperiodic signals can be viewed as periodic signals, with period going to infinity. Okay? So then the Fourier series representation sort of converges to the Fourier transform that we have now. And we were able to show many of these properties that we had for Fourier series representation also for the Fourier transform. Okay? So we went through a lot of these properties, and we spent, in particular, a lot of time on the convolution property and the multiplication property because they are important for analyzing, linear time invariant systems. Okay. Now, one last thing I want to talk about for this chapter is applying this, right, this analysis for linear time invariant systems on a specific type of systems that can be described by linear constant coefficient differential equations. Right? We talked a lot about this in the previous chapters as well. Okay. Now, in previous chapters, we didn't really, talk a lot about how to find the impulse response, okay, of this system. All right? We didn't really talk about how to find the impulse response of this system. Okay. But with the understanding that we have now, right, we're now very capable of finding the impulse response. Okay. So the way to do this is as follows. All right, so suppose you consider a linear time invariant system that can be described by this linear constant coefficient differential equation. Okay? So like I mentioned, the question here is how do we find the frequency response of this LTI system? Now there are two, closely related approaches. One is to just utilize this property here, right? Because we know that for a linear time invariant system, if you plug in a pure complex exponential, the output will be the same complex exponential times the frequency response. Okay? So if you want to find this hj omega, you just plug this inside x, plug this inside y, and when you take the derivative, suppose you take the derivative of this, right? Every time you take a derivative, you just bring down a j omega outside. Okay? So you can easily compute this derivative for however, high order you want. Okay? And similarly for y. So if you plug this in, equate the two, right, then you can find what is h. Okay. Now another approach, which is basically the same, is just to look at a general input signal x of t, but then use the differentiation and the convolution properties that we just showed. Okay? So this goes as follows. Okay. So suppose that we want to find the impulse response of this. So we can do this by first finding the frequency response. Okay? So to find the frequency response, we try to take the Fourier transform of the left-hand side, which will be equal to the Fourier transform of the right-hand side. All right, so this is what you get. Okay? Now the Fourier transform is a linear operation, so you can bring this inside the summation. Okay? So this gives you summation, okay, from 0 to n, ak Fourier transform of the kth derivative of y. Okay? And this is equal to summation k from 0 to m bk, the Fourier transform of the kth derivative of x. Okay. Now, by the differentiation property, we know that every time we take a derivative, the frequency domain has an extra j omega in the front, okay? And you can extend this to any order of differentiation. So if you have k different derivatives, right, then you just apply this k times. So the Fourier transform of this would be equal to j omega to the power k times y of j omega, okay? And similarly, this is j omega to the power k times x j omega, okay? So if you plug this inside, you then have a relationship between the input and the output spectrum, okay? Now we know that y of j omega should be equal to hj omega times x j omega, okay? So if you divide xj omega to the other side, you get hj omega, that is y divided by x. Okay? So you have this y on the left-hand side, you have x on the right-hand side, right? You take x, divide it to this side, and then this thing that is multiplied in front of y is divided to the other side. So this gives you summation bk j omega k over summation ak j omega k, here k from 0 to n, and this is k from 0 to m. Okay? Okay. So this is how you can find the frequency response of this system that is described by linear constant coefficient differential equations. Okay. Then to find the impulse response, you just take the inverse Fourier transform of this. Okay. Now, how to find the inverse Fourier transform of this, right, depends on the specific cases that you're looking at. Okay. And we can look at a couple of examples. All right. So this first example is pretty straightforward. Right? So here we have the derivative of y plus a yt equal to x of t. Okay. So following the previous approach, right, we can find that the Fourier transform should be j omega yj omega plus a yj omega equal to x j omega. Okay? So therefore, the frequency response, which is yj omega over x, is just 1 over a plus j omega. Okay? And interestingly, right, we are familiar with this form, right? So 1 over a plus j omega has an inverse Fourier transform that is a decaying exponential with exponent a. Okay? So we immediately see that the impulse response is e to the minus at u of t. Okay. Now, the second example you can do similarly. Okay. So if you again take the derivative right, divide x to the other side, you will get h of j omega, that is 2 plus j omega over 3 plus 4j omega plus, 3 plus 4j omega plus j omega squared. Okay? And you can write the denominator as the product of 1 plus j omega and 3 plus j omega. Okay? So you can check, right? So this is 1 times 3 is 3. All right, 1 times j omega plus 3 times j omega is 4j omega. And then we have j omega squared. Okay? So then once you are able to factorize this into the product of these two terms, you can then use partial fraction expansion to split this into two terms, right? So you can see that the constants 1 and 3 are different, right? So we can factor them into two terms. One is a over 1 plus j omega plus b over 3 plus j omega. Okay? So this is, again, the partial fraction expansion. Okay. So you can again combine these two terms, right? And then, once you combine these two terms, right, you try to choose capital A and capital B such that when combined, the numerator gives you 2 plus j omega. Okay? So if you solve that, the system of linear equation for A and B, you'll find that A is equal to B equal to 1/2. Okay? So if you plug this in, you'll get hj omega, that is 1/2, 1 plus j omega, plus 1/2, 3 plus j omega. Okay. And then again, these are in the form that we are very familiar with, right? The inverse Fourier transform of these are just single, sided decaying exponentials. So this has a inverse Fourier transform that is equal to h of t as 1/2 e to the minus t u of t plus 1/2 e to the minus 3t u of t. All right. So I hope this is not too difficult. This is actually quite straightforward. Right? If you use the differentiation and the convolution property, right? By the differentiation property, you can write the Fourier transform of this equation here, of the differential equation here, as a polynomial of j omega times y and a polynomial of j omega times x. Okay? So then just by taking the ratio of y over x, you can find h, right? Which you can further take the inverse Fourier transform to obtain the impulse response. Okay. Now, when you have these, systems described by linear constant coefficient differential equations, the responses are often these, exponential type, have these exponential type behaviors. Okay. So this partial fraction expansion approach, is often a useful technique in these types of problems. Okay. Now, the next example is similar. Okay. So the only reason I want to talk about this example is because it uses a slightly, different variation of the partial fraction expansion. So I won't go through the entire thing, but just to point out the difference here. Okay. So in this example, we're assuming that we're passing a signal x of t, right? This is again a decaying exponential through a system described in the previous example. Okay, so we're passing x of t through a system with this frequency response, okay, or with this impulse response. Okay. All right, so we know that this signal has a Fourier transform that is 1 over 1 plus j omega. Okay, and you want to find the output signal, right, starting from its frequency domain, y. So the frequency domain y is equal to hj omega times xj omega, okay? Now, suppose we start out from this part here, okay? So we can take this and the product of 1 over 1 plus j omega. Okay, so this gives you 2 plus j omega over 1 plus j omega times 3 plus j omega times 1 over 1 plus j omega. Okay. So this term is the same as this term. So this gives you a square on this term. So we have 2 plus j omega squared over 1 plus j omega squared times 3 plus j omega. Okay. So here is the part that's different. Okay. So here you want to again write this in using its partial fraction expansion. Okay. So originally, if you have just two terms that are both of order 1, right, you just split them into a constant over 1 plus j omega and a constant over 1 plus 3j omega. Okay. Now, when you have a higher order term here, you need to split them into multiple terms, including all the lower order terms of this part. Okay. So this will now give you 3 terms. One is A1 plus j omega plus A2 over 1 plus j omega squared plus A3 over 3 plus j omega. Okay? And then you can again, combine them. You can again combine them to find what are the values of A1, A2, A3. Okay? So this is the only thing that I want to point out here. So you can complete the rest. So just if you're not, if you want further details, you can again see the appendix on partial fraction expansion. Okay? Okay. Right, so just have to be careful when you have a higher order term here, you actually need, 2 terms to represent it, right? Actually, you need to include all the, this term as well as all of the lower order terms, okay? So having this term is not a problem, right? So we know, we are very familiar with these terms, right? These terms correspond to, complex these decaying exponentials. Right, but what about this square term? Right, this square term we also showed previously. This square term we showed here, right? So the square term we can view as the derivative of this first order term. Okay, and then you can use the differentiation property to get its inverse Fourier transform. Okay? Okay, so please do, work out the rest. Okay, work out the rest. All right, so do you have any questions with this chapter? Mm-hmm. Oh, 你说哪一行？这个为什么没有加负号？哦，因为你如果取微分的话，它会有一个负1带出来嘛，对不对？然后你也会有一个 j 带出来，所以 j 乘 j 是负1，再乘上这个提出来的负1，就是变成正1，可以吗？啊 ，OK， 好，谢谢。还有没有其他的问题？就是理论上这个系统是你设计的话，其实你会知道它的这个 impulse response 会是什么，这样。什么意思？就是说，这是因为这个系统通常是我们设计的嘛 ，right？ 那比如说你可能，其中一个为什么要讲这个例子，就是说，你如果是用一些典型的 RC circuit 拼凑出来的话，那其实它经常就是会变成是这样的一个 form，OK？ 那所以说，在这个 form 里面呢，你的这些 BK、AK 的值就会跟你的这个电容跟电阻的这些数值是相关的 ，OK？ 所以你选择了你用哪些系数的这个电容跟电阻，你其实就知道这个 equation 是什么，对，那你就可以透过我们这个方式找到它的这个frequency response 或者什么这样，所以讲完 Chapter 4、Chapter 5就很容易。Okay. 所以 Chapter 4主要是在讲说我怎么样把这个 Fourier analysis 从 periodic 的 continuous-time signal extend 到 aperiodic 的 continuous-time signal。所以主要的概念就是说，一个 aperiodic signal 其实可以看成是一个 periodic signal， 只是它的 period 趋近于无限大。OK？ 那在 Chapter 5我们只是对 discrete time 的 case 又重复再讲一次。Okay, so all of the concept is the same for the discrete time case as well. Okay. So here we're trying to extend Fourier analysis from periodic signals to aperiodic signals. Okay. So suppose that x of n is this aperiodic signal that we are interested in, right? So suppose that this is some general sequence with finite duration going from n1 to n2, right, and is 0 otherwise. So x of n can look something like this. Okay. Now suppose that x tilde of n is some periodic sequence that we generate by repeating x of n every integer multiple of the period capital N. Okay, so we take this x of n, we repeat it every integer multiple of capital N to get this x tilde of n. Okay. Now, as we let this capital N become larger and larger, right, eventually to infinity, then you can see that this periodic signal eventually becomes this aperiodic signal, right? So if you let this period become larger and larger, eventually to infinity, then eventually, as n goes to infinity, x tilde of n is just x of n. Okay? So this is the exact same idea as in the continuous time case. Okay. So suppose we look at this x tilde of n, which is a periodic signal. For periodic signals, we know that the Fourier series representation exists. So the Fourier series representation tells us that we can write this x tilde of n as a linear combination of these harmonically related complex exponentials, right? This e to the j k 2 pi over capital N times n. Right? So 2 pi over capital N, right, we can view as this fundamental frequency omega naught. Okay? Right. And then how do we find the Fourier series coefficient? Right, this is the formula for finding the Fourier series coefficient. So we take 1 over n, the summation of x tilde times e to the minus jk 2 pi over capital N times n. Okay? So as we mentioned before, this is like taking the inner product between x tilde and this complex exponential in order to see how much of x tilde of n lies in the direction of this complex exponential. Okay? And one thing you need to be careful with is that we are summing over, one period, right? We're summing over any capital N consecutive integer values of k. Okay, so this could be, 1 to n, it could be 0 to n minus 1, or anything like that. Okay? All right. Now, here we're summing over capital N samples x tilde times e to the minus jk 2 pi over capital N n. Okay. Now, when you're summing only over one period, right, you could have replaced x tilde of n with xn, right? Because xn is exactly one period of x tilde, okay? And then you can extend the summation to infinity because, xn is 0 beyond one period, okay? So this summation, originally only over capital N consecutive integers, now is extended to infinity by replacing x tilde with x. Okay? All right. Now let us define this capital X as the summation of xn times e to the minus j omega n. Okay. So if you compare this with this here, then this summation is actually just capital X of e to the j omega at omega equal to k omega naught. Okay? So this term here is actually x of e to the j k omega naught, where omega naught is 2 pi over capital N. Okay? So if you do replace the summation with this capital X, then AK is just 1 over N times this capital X at k omega naught. Okay. So if you plug this inside here, okay, if you plug this inside here, x tilde of n can be written as the summation over one period, 1 over n x times e to the j k omega naught times e to the j k omega naught n, right, which is this, okay? All right. And then we can write this 1 over n, right? If I multiply it by 2 pi, right, and divide it back, this 2 pi over capital N becomes omega naught. Okay? So I multiply this by 2 pi and divide it back in the front. I will get a omega naught here. Okay. So then what is this? What is this? Okay. So if you look at this particular value here, right? This is the function x of e to the j omega times e to the j omega evaluated at the point where omega is k omega naught. Okay? So this term is essentially this function here evaluated at the point k omega naught. Okay? And you can show, I'll probably have to show this tomorrow, you can show that this summation eventually converges as omega naught goes to 0, converges to a Riemann integral of this function over one period. Okay, over one period. Okay, so let's do that tomorrow.